In this chapter, we're going to look at testing linear restrictions. This corresponds to chapter 5. Okay, suppose the true model is this one here. So we have 3 beta coefficients, and this equation represents the fitted model. So in the fitted model, you have beta hat. These are the estimates, and then this is the fitted residual. As we discussed earlier in the previous chapter, beta hat is random because it depends on data. Even if we're making the assumption that x's are non-stochastic, which is non-random, the beta is random because it also depends on the y, and the y depends on the epsilon, and epsilon is assumed to be random. That was my t. And the true beta is not random. The true beta those are numbers that we're trying to estimate. And when we're testing a hypothesis, we're trying to test a hypothesis about the value of the true parameter. Okay, so define beta hat OLS to be the fitted model coefficients and beta to be the true model coefficients. So the true ones are unknown. In previous chapters, we obtained the distribution of the OLS estimator, right? And this was the variance expression that we derived. And we're going to use this to derive statistics for testing hypotheses about the true betas. Okay, we do not know exactly the variance covariance matrix. We know x prime x, but we don't know sigma squared. And this is the estimator we will use instead. Okay, so let's first look at hypothesis tests about one regression coefficient. So suppose we just want to test is beta 3 equal to 0. And the alternative is beta 3 not equal to 0. So to test this hypothesis, we can just use the distribution of beta hat 3, okay, or beta j or whatever, beta hat j. Okay, so beta hat j is normally distributed, with this beta j, the true parameter, and then sigma jj is the jj element of the sigma matrix. Okay, under the null hypothesis, it has this distribution. So we're plugging in the null, the fact that beta j equals 0, that's under the null here. Okay. So for right now, we're just going to assume that we know the sigma matrix. So in practice, if you have a small sample, the sigma matrix estimation can make a difference, and you get a you get an F distribution instead of chi-square if you set it up as a chi-square test. But for right now, just assume that we know it, or that the sample size is large enough that we don't have to worry about the estimation, because it complicates matters a little bit. All right, so the test statistic for testing the null hypothesis, we want to come up with something that's normal 0, 1, because then you can actually compare it against a normal statistic that you get using R, like 1.96, something like that. Okay, so you form the test statistic, and for a two-sided test, so the alternative is just beta j not equal to 0, and at 5% significance level, we reject the null hypothesis if the absolute value of z is greater than 1.96. Okay. We can also do a test not against the null that it's 0, but against the null that it's some other number. Okay, and so in that case, the test statistic would look like this. So here we're testing beta j equal 2. Okay, oftentimes we'd like to do hypothesis tests on multiple coefficients, not just one. Okay, and the built-in software does not always allow you to do this. You might have to set this up yourself, right? With the built-in software, you could do these sorts of tests pretty easily. I mean, this you can do just looking if the estimate coefficient is at least 2 times the standard error. That's the rough guide, and you can do this in your head, just looking at the coefficient and the standard error. This test, you also have all the ingredients to do pretty easily, but we we might want to do different types of tests. So for example, suppose we have a Cobb-Douglas production function model. So output, is equal to some alpha. Alpha is like a technology parameter. Labor input, well, this is A. This is labor and this is capital. Okay, and one hypothesis that's interesting to test is if alpha plus beta equals 1, because that's the case of returns to scale. No return. Right, no returns to, well, returns to scale, constant returns. Yeah, that's what I meant to say. So if beta 1 plus beta 2 equals 1, then we have constant returns to scale. Okay, it could be greater than 1, it could be less than 1, but usually people test if you have constant returns to scale. Okay, so let's look at how you would do this type of test. Oh, and then also within the Cobb-Douglas model, in order to implement this, you normally also add an error term. And that accounts for like unobserved factors affecting production. Okay, so we're going to need some properties of what are called quadratic forms in order to do these more complicated kinds of tests. Okay, so for a random variable v, and this is usually going to be a vector with some normal distribution, mean 0 and variance omega, if we pre-multiply by a, then the distribution is going to be given, AV is going to be mean A mu and variance A omega A prime. I think we already covered this actually in a previous set of slides. Okay, so now this is another thing we're going to be using. Like suppose we have some vector z, which is normal, mean 0, variance identity matrix. Okay, so these are independent normals. So if we do z prime z, that's basically going to be summing up the z's. Okay, and the distribution of the sum of squared independent normals is chi-square, and the degrees of freedom is the number of terms in the sum. All right, so just keep that in mind. Now suppose we have a different random vector y. It's normal, mean 0, not with the identity matrix, but with sigma squared times the identity matrix. Then we can transform the y by dividing by sigma. Okay, and that's also going to be normal, 0i, and so this transformation is going to have a chi-square distribution. Okay, so where the sigma y inverse is equal to sigma squared I. Okay, so these types of statistics are called quadratic forms. Okay, and more generally, if you have a y with some mu and it has some general variance matrix, it doesn't have to be sigma squared I, just some general omega, then this quadratic form is going to be chi-square with r degrees of freedom. Okay, where r is again like the number of terms when you do y prime y here, or y prime, well, in this case, in this more general case, it takes this form. But it's the number of rows of y, basically, is r. Okay, so let's look at how we're going to now apply those results about quadratic forms to do a test of a joint hypothesis within the regression model. Okay, so, and this is just an example. Suppose you want to jointly test it's beta 1 equals 0 and beta 2 equals 0. And the alternative is that either beta 1 is not equal to 0 or beta 2 is not equal to 0. Okay. So you can express the joint hypothesis in this way. Okay, and note that the first row, this just multiplies by beta 1, so that's beta 1 equal to 0. And the second row is beta 2 equal to 0 here. Okay, so this that was the hypothesis we want to test. Okay, and we're not saying anything about beta 3. If we wanted, we could add on something about beta 3, like beta 3 equal 3 or something. But here we're only testing hypothesis about beta 1 and beta 2. So 3 we're just kind of ignoring here. All right, so if beta is normally distributed with mean beta, or beta hat is normally distributed with mean beta, variance sigma, using the properties of quadratic forms, we get this distribution for R beta, where R is this, and this is called a restriction matrix. That's why it's called R, because it's capturing the restrictions we're testing. Okay, it has this distribution, and this just using those properties from the earlier slides about quadratic forms. So to test the null hypothesis, so the null hypothesis we wrote as R beta equals 0, right? Looking back here, R beta equals 0, that's the null. So we're going to impose the null. So under the null hypothesis, this should be the distribution of R beta hat. Okay. All right, and we can set this up as a chi-square distribution, like using those results about quadratic forms. Okay. So this is sort of like the y that we had before in the previous slide. And this is the variance. This is actually the variance matrix of R beta hat. Okay, so we have R beta hat prime, this quantity prime. Here's the variance matrix inverse, and then R beta hat. And the degrees of freedom is going to be the number of restrictions we're testing. So in this example, where we're just testing beta 1 equals 0 and beta 2 equals 0, the degrees of freedom is 2. Okay. So Q equals 2. It's usually the number of rows of the R matrix. That's how many restrictions. It's not the number of betas involved, okay? Because if we tested like beta 1 plus beta 2 equal 1, that's only one restriction. Okay, it's really the number of equations is the number of restrictions, not the number of betas involved. So just keep that in mind. And it usually corresponds to the number of rows of the R matrix. Okay, so in general, if we want to test R beta equal little r, so a lot of times little r is 0, but it doesn't have to be 0. So for example, if we're testing constant returns to scale, then little r is 1, because we're testing whether the sum of the betas equals 1. Okay, so generally we would plug in the null here, okay, because we're plugging under the null, and that would be the distribution under the null. And again, we can set up as a chi-square statistic. So when you need to do a normal statistic and when you need to do a chi-square statistic? Well, if R just has one row, then you see this is just, and this is k by 1, and this is going to be like number of restrictions by k. So if there's only one restriction, then this would be a 1 by 1. And in that case, you could do a normal test. You don't have to do a chi-square. But if R involves more than one row, so you have multiple restrictions, then you can't just do a normal test. In that case, you have to do a chi-square test. Okay, but for the case where there's one restriction, so Q equals 1, you have the choice to do a normal test or a chi-square test. And this chi-square statistic is actually just going to be the normal statistic squared. So for example, 1.96 squared is the cutoff for a chi-square 1 degree of freedom. Okay, so notice that this test statistic, if the null hypothesis is not valid, so R beta hat is not equal to R, then this test statistic gets large. Okay, because this then would be not equal to R. Okay, and So this would just be some number, and this variance is actually getting smaller, and we're taking the inverse. So this is actually getting big. So the test has power under the alternative because the statistic is getting large under the alternative. Okay, so that concludes the chapter about hypothesis tests. It's a good idea maybe to try to do the exercises at the end of the chapter, because, like, for example, it would be good to do the set up the R matrix for the constant returns to scale assumption, right? That the let's see, this is this test here. That alpha, the test would be, see here, alpha plus beta equal 1, or when you take the logs, then the beta naught is equal to log of A. Beta 1 would be alpha, and beta 2 equals the beta here. I mean, I guess I shouldn't have used beta. We should probably call this theta or something because it's not the same beta. But just testing the constant returns to scale would be this plus this equals 1. So that would be one test. And the R matrix should just have a 1. Well, for the intercept, you're not doing anything. So it'll be like a 0, a 1, and a 1. That's what the R matrix will look like. So it would be good to try to set that up.